Hey everybody. Today we're going to talk about Unit 12, which is chemical kinetics, and more commonly referred to as just like reaction rates. We've talked about chemical reactions a lot. This chapter is all about the speed at which they happen. Some reactions happen like nearly instantly, some of them take days or weeks to react fully. Today we're going to learn a little bit more about that. Please complete your Unit 12 notes along with the video. This one's a little bit shorter than the last one, which is good. A very math heavy chapter. So you'll actually notice in your notes packets, when we're about halfway through, there's a giant sheet of formulas. So most of them will be given to you on my tests and on the AP exam. So there's not a lot of memorization you got to worry about. But knowing how to use them is kind of tricky. There's a whole lot of formulas. So we're going to go ahead and get started. Talking about rates of reactions, rate laws, mechanisms, and catalysis or catalysts, as you probably heard of them before. We're going to start pretty basic with average rate. Now, this is something you may or may not have known, but you've done a lot of times in your math class, finding the average rate of a unit over time. So here in yellow, I have the formula for rate, and it might look similar to things you've used before. It is this thing in brackets, this A in brackets, that stands for whatever reactant we're dealing with. And the brackets just means the concentration of. So we're looking at the concentration of something 2, which is like at a second point in time, minus A1, our initial concentration, divided by time 2 minus time 1. Or in other words, it's the change in concentration over the change in time. Now this formula, we're not going to use it a whole lot, honestly, but this is how you basically would calculate a rate for any sort of class. This is exactly what you do in like math class when you calculate slope. Y2 minus y1 over x2 minus x1. That's exactly what we're going to be using with our data here on the right, except for just applying it more to our class by using concentration versus time. Same concept though. So a couple examples. Over here on the right, I have a data set for my reaction A yields B, or A turns into B. I have my time, 0, 20, 40, 60, just my time after my reaction starts. And then you'll notice my concentrations of A and B. Now looking at A, it's a reactant. So it makes sense that as the reaction goes forward, you're going to start running out of it. You're using up some of A to produce B. So if you look at A, it starts at 1 molar, then goes to 0.54, 0.3, 0.23, and you would imagine eventually after a couple of minutes it would be at 0. And then the opposite will happen for B. It starts at exactly 0. You have no product to start with. But after a while, it starts to accumulate more. Okay? You'll notice the rate isn't entirely constant. It's not constantly reacting at the same rate. If you look, it's actually slowing down a bit. The first 20 seconds, almost half of it reacts. But then the next 20 seconds, only a little bit more reacts. And then the next 20 seconds, even less reacts. So this reaction kind of slows down as you run out of reactant. The more reactant you have available to react with, the faster the rate of the reaction. So most reactions you'll notice will slow down over time. Well, my example here, I want to calculate the average rate of A during an interval from 20 to 40 seconds. So I want to see how it changes in between 20 and 40 seconds. So we're going to just apply that formula. We're going to go A2 minus A1 divide by time 2 minus time 1. Now A2 is going to be our second concentration. So that's going to be our concentration at 40 seconds. So I'm going to go to my table, and that is 0.3 minus A1 is my concentration at 20 seconds, which is 0.54. 0.3 minus 0.54 divided by time 2, 40, minus time 1, 20. Okay. Now, if you swap which one you make time 1 and time 2, your answer won't change very much, but the sign of it might change depending on if you don't do it completely right. So that's what I'd recommend, is making 2, whatever the second value listed in the problem is, or the higher time, and then T2, yeah, it's going to be the time later. I'm going to plug all this into my calculator. When I do, I get a negative number, 0.012. Molarity per second is the unit. That's the molarity over time. And I get a negative number here, which makes sense because I'm calculating the rate of A, which is going down. And negative signs just represented you're actually losing amount of this. So that answer looks good. We're going to do the same thing for the rate of B over a different interval from 0 to 60 seconds. So I'm going to go from the very beginning to the very end. So very similar to what we did here. B at time 2 minus B at time 1 divided by time 2 minus time 1. Right, we just have our dependent variable over our independent variable, just like you do in math. Plug in my numbers. B at time 2 would be at 60 seconds. That I get 0.73. Minus at 0 seconds, it was 0. Divided by 60 seconds. Plug it into my calculator for a moment. And I get a very similar answer. .012 molarity per second. Slight mistake that I'm noticing now on your paper. Your data table is going to look slightly different. It says 0.77 instead of 0.73. Doesn't really matter. We get the point across. You're just doing whatever this time says. So my data table might not match up exactly with yours because I edited yours but forgot to edit mine, etc. So your numbers might look slightly different. It's all the same. Okay. This time we have a positive number because we're increasing the concentration of B over time. So that makes sense. Like I said, the rate of a reaction is not always constant. A reaction may occur rapidly at first, then slow down as reactants are consumed. We're going to talk about a bunch of different ways reactions can happen. Sometimes it is constant. Sometimes just from beginning to end, it's a constant speed and it doesn't change. That's actually called a zeroth order reaction. And then sometimes it is constant, sometimes it's exponential. So we'll talk about all those things. Average rate is a rate over time. Instantaneous rate is the rate at one specific time. A couple ways to go about this. If you're in calculus or have taken calculus, this would be a little bit familiar to taking the derivative at a point to get the slope at that point, essentially. Or if you've drawn tangent lines in math, it's the line tangent to the curve at that point. So if we look at this graph real quick, I want to know the rate at one specific time. I can't use that previous interval because I don't have two different times to subtract from. So I could draw a tangent line instead. So I have here, I want to know the slope I want to know the rate at this point, and it's just going to be whatever the slope is at this point. So I draw a tangent line, which is a line that runs exactly parallel, touches that point very gently, and then just runs off in a parallel. I could take the slope of that line, and that's equal to the rate at that time. If I want to know it at this point, I draw a tangent line like this and measure the slope of it. Okay. One sec. On instantaneous rate, you will not need to use calculus to calculate it exactly, but we're going to estimate it occasionally. So we'll talk about in class about how to estimate instantaneous rate. But if we just look at one of these graphs, say I wanted to know the instantaneous rate at 30 seconds. 30 seconds isn't on my graph here, okay? But I could estimate it decently. If I found that the rate from 20 to 40, I'd assume that 30 would be somewhere in the middle of that. So the average rate from 20 to 40 would be pretty similar to the instantaneous rate at 30, but not exactly. So in class or on a test, I might ask you to estimate the instantaneous rate at a certain time, and you could just do it at the two numbers around that time to just get a decent estimate of what it would be. Okay, here's another example, running another reaction. For this reaction at 25 degrees Celsius, ammonia, if you're not familiar, that is NH3's common name. Like water is H2O, it's one of the ones we definitely should know. NH3 is ammonia, so it's our product. We can figure that out from the context because it says it is produced and it's our only product, but make sure you know that one. and it's produced at a rate of 0.05 moles per liters times second, or molarity per second. That's the rate it's produced at. It's a positive number because it's being produced. What are the rates at which nitrogen and hydrogen will be consumed? And then it gives us our balanced reaction here. We can see the rate that we're making in H3. We want to see if we can figure out how fast we're using N2 and H2. Okay. We can use some stoichiometry here to help us. On your formula sheet, you're given a formula that looks like this. And I hesitate to give it to you because it does look kind of confusing, but it's like 1 over A times concentration of A, that whole thing's negative, equals negative 1 over B, concentration of big B, equals 1 over C, concentration of C, that one is positive, equals 1 over little d, concentration of capital D, positive. And that's saying for any general reaction, little a, plus little b, gives you little c, that's supposed to be a plus, little d. This is a general reaction. It's products A's and B. Sorry. A and B. The lowercase, that's talking about the coefficient. So just however many of them you have. For a given general formula like this general formula at the top, it works to give you, the conversion between all of them. So if you use this formula, you could figure it out. But that's a little bit weird for me. I just like to look at it like I'm doing a mole-to-mole ratio. So I have my N2, 3 H2s, gives me 2 NH3s. So my NH3 is being produced at a rate of 0.05. But there's a 2 here. And I keep in mind that 2 means every time one reaction happens, 2 of them are produced. Okay, my reactants over here are going to be used at the same ratios. But every reaction only uses 1 and 2. What that means is I'm consuming not 0.05, but half of that, 0.025. This rate is going to be half of this rate because every reaction produces 2 of these, but only consumes 1 of these. So that's an easier way for me to just think about it instead of trying to plug everything into this long formula. Now, over here with H2, I consume 3 of these every time. So the rate of this is going to be 3 times the rate of N2. I'm using 3 times as many. So I'm using negative 0.075. I made them negative because I'm using them up, whereas this one is a positive. Okay? Basically, I'm just paying attention to the stoichiometric ratios to figure that out. I can do a unit conversion sort of thing if I want. I could do if I wanted to go from, I have 0.05 in H3s and I wanted to find how many H2s, what the rate of H2 consumption was, I could go 0.05 is the rate of NH3, and then just do a mole-to-mole ratio. I could do NH3 on the bottom, H2 on the top. I use 3 H2s, so I'd put that there. 2 NH3s, so I put that there. I put in the mole-to-mole ratio, multiply, and I get the same answer. But I do need to remember I need to make it negative because I'm consuming this. Okay, so that won't be taken into consideration if you use that method. Any way you think about it, I just recommend kind of thinking about it like this. How many of them am I using per reaction? How would that affect my rate? Okay, on to rate laws. Rate laws are great. Writing them isn't too bad, and it's a very common question on the AP exam. So it's usually an easy way to earn 1 point on a question, even if you have no idea what the question's talking about. A very common question is write the rate law for this reaction. That'll be part A, and then part B will be insane experiment that you have to design or something like that. But you can get part A. Okay. Shows how the rate depends on the concentrations of reactants. for the composition of nitrogen dioxide, I start with my reactant. That's really all you care about when writing a rate law, is the reactant. The products, you assume you start with none of them, so it's not really going to influence how fast the reaction happens. Rate equals K. K is a rate constant. It must be determined experimentally. It depends on everything in the reaction, what temperature it's happening at, what's the pressure, what reactants do you have, what products are you trying to make, what state of matter are they in. The rate constant is just basically how fast the reaction happens, but you can only determine it experimentally. You can't even look it up in a book. N is the order of the reaction. The order is referring to how important this reactant is for the reaction going forward. It'll be 0 order, first order, second order, third order. A 0 order, we're going to talk about in a second, but would mean that it doesn't affect it at all. And a second order means it affects it exponentially. First order means it affects it normally. So we're going to talk about all those different things mean. Very important. These values, K and N, are determined experimentally. You can't just write it from an equation. You have to do some analysis of some results. All right, a couple different types of rate laws. First, differential rate laws. That's what we're going to talk about first here. It's also what we just call a regular rate law. It shows how the rate of the reaction depends on concentrations. It'll always be written in this form. Rate equals K, and then you're going to put your reactants in brackets with different exponents depending on stuff we're going to talk about. Rate constant is our K. It's a constant for a particular reaction at a specific temperature and other conditions. The N and M are the orders of the reaction. It'll be an integer or a fraction. We'll talk about how to determine that. The other type is an integrated rate law. It shows how the concentration of species in the reaction depend on time. Integrated rate laws, we're going to use these. They're more complicated. You derive them using calculus. We don't have to do the derivations ourselves, but they tell us a couple other pieces of information about them, which we'll talk about. Okay. Determining the form of the rate law. The order of each reactant, N, must be determined experimentally. We'll consider 3 cases only. Only 3 we really have to deal with, because only 3 we can actually figure out reasonably. 0 order, first order, second order. A 0th order reaction means your exponent is 0. If your exponent is 0, whatever your thing is equals 1. So it basically doesn't affect it at all. A change in reactant concentration has no effect on the rate. So it doesn't matter if I start with a whole bunch of my reactant or just a little bit, the rate will be the same regardless. Rate stays the same for varying concentrations. The most common is first order, N equals 1. Changing the reactant concentration has an identical effect on the rate. Okay, so if I double my amount of initial reactant, I double the rate. Or if I have the amount of initial reactant, I have the rate. The rate doubles when reactant concentration doubles, or if I multiply by 10, the rate multiplies by 10. Second order, changing the reactant concentration will affect the rate to the square of the change in the reactant. Basically, rate is quadrupled when reactant concentration doubles, is what that should say at the bottom there. So if I times 3 my initial concentration, my rate goes up times 9. Or I could cut it in half, and it would go down to a quarter. So there's an exponential effect by the amount of reactant I start with. We can determine the overall reactant order by adding up all the exponents in a rate law. So whatever all of those exponents are, add them all up together, and that's the overall order of the reaction. So if A is first order and B is second order, the overall reaction would be third order when you add them all up. Okay, this is the most common type of problem we'll see with rates. Down here I have a example of a data set from an experiment, because we have to determine this experimentally. The question says the order of a reactant is the power to which the concentration of the reactant must be raised to produce the amount of product indicated by the reaction. Observe the following data for the reaction. Okay, I have 3 trials, and each of the trials I've changed the amount of A and the amount of B that I started with. I need to know how does A affect the rate and how does B affect the rate. Notice I don't care about C or D because they're products, so they don't really affect anything. But A and B will be different. And we've strategically tested it and compared the rate of the reaction based on our starting conditions. Okay? All right. What you'll notice, let's look at trial 1 and trial 2. Between trial 1 and trial 2, I've doubled the amount of A. I started with 0.02, went to 0.04, while I held the amount of B constant. What this means is I can see how doubling A affects the rate of the reaction to learn more about it. Okay, so I've doubled the amount of A. I want to see how the rate changes in response to that. My rate goes from 0.003 to 0.012. It multiplies by 4. When I double A, I quadruple my rate. And what that means is this is a second order reaction in respect to A. That means A is second order. Now we're going to look at the inverse. Between trial 2 and trial 3, I hold A constant. Then I double B, so I can see how just B influences the overall rate. When I double in my concentration of B, my rate goes up from 0.012 to 0.024. It also doubles. So when I double B, my rate doubles as well. Therefore, it is first order with respect to B. Okay? The rate law for this equation is written rate equals K, A squared, because it was second order with respect to A, B just to the first, because it's first order with respect to B. The overall reaction is the sum of the individual orders, and therefore it's third order. So I'd use that experimental data to write the rate law and to figure out the overall order of the reaction. Okay, that's the most common type of problem. We'll practice that a bunch. Now we're going to talk about integrated rate laws, and there's a couple of weird things in these. The reaction rate depends on concentrations to the first power. Here I'm writing out the rate law. Rate is the change in A over the change in time, the change in concentration over time. And that's equal to K, the rate constant, times A to the first. So this is what our formula would look like for a first order rate law. Just a concentration of A to the first is the change in A over time. Calculus magic allows you to integrate this. Take the integral of both sides, do a little fancy math, and you get this formula from it. So this is I'll show you the derivation in class if you want to see it. I had to do it myself because I couldn't remember how to do it. But this is our new formula, basically. The second formula on the bottom, ln of A equals negative KT plus the ln of A initial concentration of A. If you're confused where the ln's came from, it's just calculus magic. Don't worry about it. All of my variables I have here, A with no subscript is just the concentration of A at whatever time you care about. K is our rate constant, that's still there. T is time. And then AO is my initial concentration of A. This is another formula that we're going to use for a purpose in just a bit. Okay. So, okay. Here is the plot of the ln of N2O5, which is just our reactant versus time. We're going to graph the time versus the natural log of this number. When this is graphed, you notice it's a straight line. And that's basically what this is used for. If the graph of time versus the natural log of something is a straight line, that tells you it's a first order reaction. If it's not a straight line, then you don't know what the reaction, you don't know what order it is. It could be 0, could be second. We'll have to test another way. With the example, I'll kind of show you what I mean by this. But just know for now what you're looking for is if you graph this equation and it's a straight line, then you know it is first order. The slope of this line is going to be equal to the negative of the rate constant. So it's a negative because it goes down, but if you find the slope of this, that is your rate constant. So this is a way you can determine the rate constant experimentally. You record the time over a certain amount of time, you record the concentration, which you take the natural log of, plot it all, and record the slope of the line, and then that will be your rate constant for that reaction. Okay, for second order, we have change of a over time is equal to k a squared. We're going to do calculus magic again to integrate this, integrate both sides, and you get 1 over a equals kt plus 1 over a naught, or initial concentration of a. If we graph this one, 1 over a versus time, for a second order equation, you'll get a straight line as well. Okay. So basically, if you take your time and you graph it versus 1 over your concentration, and the line comes out perfectly straight, then it's a second order reaction. This is basically all the integrated rate laws are used for, and I will show you more on this on the example we're about to do, and we'll talk about it a little bit more in class, because I know it's kind of weird. Okay, we're also going to talk a little bit about half-lives in this unit. So we have talked about half-lives a bit before with like radiochemistry or something like that, but we talk about it with the rate as well. And there's actually a couple different half-life formulas. The most common one is this one, the first order half-life. This is generally how we think about a half-life. It's the time required for a reactant to reach half of its original concentration. This formula, I prefer the one on the right here, the time 1/2. That's the time of a half-life, equals just this number, 0.693. That number is just the natural log of 2, divided by k. K is the rate of the reaction. Half-life doesn't matter how much you start with. The time of a half-life is constant. We've done half-lives a little bit before, with talking about things like radioactive carbon-14. Carbon-14 has a half-life of like 5,800 years. It doesn't matter how much of it you start with. That's just a fact about carbon-14. I could start with 1 million particles. I could start with 1 million tons of it. Half of it is going to split in half, or it's going to split in half every 5,800 years, regardless of how much I start with. And that's what a first order half-life is. The initial concentration doesn't matter. So I can solve for our original half-life just by using this formula here. I need to know either the length of the time of one half-life or my rate constant to figure it out. Second order half-life is the exponential half-life. The half-life of a second order reaction does depend on the concentration remaining of the reactant. The time of a half-life here ends up being 1 over k times the original concentration. I'm not going to concern you with where this formula comes from. It's also from calculus magic, so just go with it. Basically, with a second order half-life, it's exponential. So if you start with a ton of it, the half-life is going to be faster. But if you start with just a little bit of it, the half-life is going to be slower. So this one, the half-life actually changes over time. Okay, let's look at a couple examples of these. It says in a second order reaction. That means I'm going to use my second order half-life. So I'm going to go ahead and write that down. Time 1 of the half-life equals 1 over k times my original concentration. If it said first order, I would use the first order half-life. Time of a half-life equals 0.693 over k. But this is second order, so I'm going to use this one. It took 112 seconds for 50% of a substance to decompose. That's the definition of a half-life. So that 112 seconds is the time it takes for one half-life to pass. Okay. If the initial concentration was 0.2, what's the rate constant? So I'm looking for K, the rate constant. My initial concentration was 0.20 molar. I'm just going to solve this for K. So, looking for my work. Pull my calculator. Okay. We're going to solve this. We're going to multiply both these numbers up here. So we're going to get 112 times K times 0.20 equals 1. I'm going to multiply these two together. And I'm going to get K times 22.4 equals 1. Divide each side by 22.4. I get K is like 0.0446. That's the rate constant for this reaction. Okay. In a first order, that should say, it took 112 seconds for 50% of a substance to decompose. If the initial concentration was 0.2 molar, what's the rate constant for this reaction? So this is first order, so I'm going to use the first order rate law this time. My half-life time is still 112 seconds. That's equal to 0.693 divided by K. Well, my initial concentration is given to me, but it doesn't matter because I don't put it into this reaction. So this one I just solved like this. They could have said the initial concentration was 1 billion tons. That wouldn't have mattered. So multiply out my K. I'm going to do my math. I'm going to do 0.693 divided by 112, and I get 0.00619. So your rate constant, it really matters which formula you use. I will definitely write one like this example on your test that includes too much information to try to persuade you to use the wrong formula. But remember, first order reaction, this one, first, second. There's also a 0th order one, but we're not going to worry about it. And there's a 3rd order one, etc. The 0th order rate law, that means rate equals K times A0, but that's just 0. So when you integrate, you get this expression, A equals negative KT plus AO. That looks like slope-intercept form, because that's essentially what it is. If you graph this and you get a straight line when you just graph it just like this, then you know it is a 0th order reaction. Let's talk about what all those things mean. Let's look at this example. So this is what the integrated rate laws all are used for. The first, second, and 0th that we just talked about. We have 3 different formulas, and we're going to figure out how to use that information. The following data was obtained for the reaction of decomposition of nitrogen dioxide in the gas phase at 300 Celsius. That doesn't matter, let's just look at our formula. NO2 becomes NO and half a mole of O2. Sure. Determine the rate law for this reaction and the value of K. The reaction, the temperature, the gas phase, none of that matters. We're just looking at this data here. I have my time, 0, 50, 100, 200, 300. I have my concentration of NO2, which was recorded at each of those times. I want to figure out what's the order of this reaction. It's going to be 0, first, or second. So if I graph just this data it gives me now, and it makes a straight line when I do, it's 0th order, because this is just the original concentration of NO2 versus time. What that would mean is this happens at a constant rate, regardless of concentration, regardless of how much NO2 I have. I'm going to take the natural log of the NO2, though. If I take the natural log of NO2, I'm going to take the natural log of this number, find that. I'm going to do it for all of my points, take the natural log, take the natural log. If I graph time versus all my natural logs, and it's a straight line, then it's a first order reaction. And then finally, I'm also going to do it with my 1 over NO2. I'll just do 1 divided by this number to get my value for NO2. And I'll repeat it for each of these 5 values, do 1 over NO2, and then graph time versus 1 over the concentration of NO2. If that makes a perfectly straight line, then it is a second order reaction. Okay, so that's exactly what I've done here. I've gone ahead and just filled out all of my graph without graphing any of them first. Fill out my table. I've taken the natural log, okay, and I've taken the 1 over, and I've gotten this whole table filled out. And now I'm going to make 3 separate graphs. One that graphs this dependent variable, one that graphs this one that graphs this one. I have those graphs there for you on your paper so you can kind of look at all of them. So this first one here, this is for the original data, just my concentration versus time. When it's graphed in blue, you see it's a pretty straight line, but it definitely has a curve in it. It's not a perfectly straight line, therefore this reaction cannot be 0th order. The natural log gets us even closer. We take the natural log, graph it over time, and you have a fairly straight line, but it's not perfectly straight. But if we go to the second order test, 1 over my concentration versus time, it makes a perfectly straight line. So therefore, graphing all this, I can figure out my reaction is second order experimentally using the integrated rate laws. I can write my rate law to be rate equals K NO2 squared, because I figured out it's second order. it was first order, I'd put a 1, and if it was 0th order, I'd put a 0, which would make rate just equal to k. That's a lot of work for a problem. We're going to do one example of this in class as well as we can. We're going to probably let a piece of technology graph all this for us, though. Doing this by hand is extremely tedious. On your next page, you have this table printed out for you. This has all of your different useful variable, all formulas and stuff like that for 0, first, and second. First, it has your rate laws, which is what a general formula rate law would look like. For the 0th, the rate that's just equal to the rate law, or to the rate constant, excuse me. For the first, it's equal to a to the first power, and for seconds, a to the second. You have your 3 integrated rate laws. These actual formulas don't really matter that much. You're graphing these formulas, but honestly, I believe that it's just easiest to just, for the 0th order, just do a. First order, just do ln of a. Third order, just do 1 over a. The right side of this equation doesn't really matter. Just kind of remember the left part here. What's y equal to is really what matters. Okay. Straight line plot would be a versus time, ln of a versus time, 1 over a versus time. The slope of the line, it is going to be negative for the first two because both of those lines would be pointing down. And it'd be positive for the last one because the 1 over is going to make it go up. Then we also have half-life formulas. We didn't talk about the 0th order one. Here it is if you want it. We're not going to use it in class. We're going to stick to first and second order. These are the 2 equations we need to know. All right, kind of the last, getting into the end of it here, we have reaction mechanisms. Most chemical reactions occur by a series of individual steps called elementary steps. For an elementary step only, the rate law can be written from its molecularity. I'll show you what that means, and it makes it really easy. If I tell you that a reaction is elementary, that means it happens in a single step, and it's really easy to write the rate law. Most of the time, it won't be that nice, though. So, who cares? But let's talk about it real quick. Molecularity is the number of species that must collide to react. Unimolecular means just one molecule. Like literally one molecule must collide to react. Bimolecular is 2 molecules. Termolecular is 3. Sure, I don't care. We want to write the rate law of this elementary reaction below. I'm not given any data. I'm not given anything to help me with it. I'm given the fact that it is elementary, and that's really what I need. It is elementary, so all we have to do is write the rate law. Start with the rate equals k. And let me write down this reaction. First of all, no one cares about the products, so I'm just going to cross that off. So pretend this says rate equals k. I'm going to look at N2. Based on just its coefficient is how you can determine its order. There's a 1, so this is going to be to the first. Next is going to be H2 is my next reactant. Its coefficient is a 3, so it's to the third. That's only allowed during an elementary reaction. But writing the rate law of an elementary reaction is on the AP exam sometime. If that's the case, you just take whatever coefficients they have here and write them up here as the order. This reaction would overall be 4th order because I'm 1 plus 3. Yep. Okay. Reaction mechanisms usually have multiple steps though. The one we're really looking at to help us write rate laws is called the rate determining step. A reaction is only as fast as its slowest step. It's basically the bottleneck of a reaction. If I have 10 reactions in a row, whichever one is the slowest is going to determine how fast the reaction can happen, because the reactions that happen after it are just going to be waiting for the slow reaction to finish anyways. The rate determining step is the slowest step. It determines the rate law and the molecularity of the overall reaction. Here is an example. I have 2 steps. This is a reaction mechanism. It's not elementary because it happens in multiple steps. From the equations below that describe the 2 elementary steps of a process by which a certain chemical reaction occurs, write the rate law and the balanced chemical reaction of the overall equation. Let's write that down. So we have step 1. I have 2A plus B yields 3C plus D, and it gives us the information. This is the slow step. Cool. Step 2, 3C yields E plus 2F. This is the fast step. All right. Couple of things the problem wants us to do. It wants us to write the rate law, and it wants us to write the overall reaction. The rate law, it's very tempting to write the overall reaction by adding all of this together and then writing the rate law. To write the rate law, all you need to do is find the slow step. Use its reactants in just the slow step to write the products, or to write the rate law. So, rate of this entire thing equals K. The slow step is A, 2. So this is going to be A squared. B just has 1, so it's just B. That is the answer to the first part. I ignore all of step 2 because it's the faster step. Look at just the rate determining step, which is the slow one. Use its reactants, write the rate law. Now, the second thing it wants me to find the overall reaction. So I'm just going to add these two together. The 3C will cancel on either side to give me a final reaction of 2A plus B yields D plus E plus 2F. That'd be my overall reaction. (3C), our C, is going to be called our intermediate. It is something that's made during the reaction that's also consumed before the end. Essentially, it won't show up in the overall equation at all. It's a molecular atom present in a reaction sequence that is neither a reactant or a product of the overall reaction. Couple of topics at the end. First, we have the collision model. It's the central idea is that molecules must collide to react. Molecules will only react not just from being adjacent to each other, they're all moving around in their solution really fast. Only when they bump into each other, they will react. However, only a small fraction of collisions result in a reaction, and there are 3 main factors that affect whether or not 2 molecules colliding will react. First is the activation energies. How much energy does this reaction need to start in the first place? Sometimes when molecules hit each other, they're going barely fast enough for a collision to occur, or for a reaction to occur. Sometimes they're speeding into each other, and there's a lot more energy behind their collision, which allows the reaction to start. The temperature really affects the activation energy as well. The temperature is how fast the average particle is moving. The faster they're moving, the more likely their collision has enough energy to overcome activation energy and start a reaction. And last here is molecular orientations, which is basically, are your molecules running into each other enough? Are they facing each other? And has a catalyst helped them orient themselves to help reactions occur, like to kind of stimulate reactions? First, activation energy. It's the energy that must be overcome to produce a chemical reaction. If reactants do not have the minimum energy needed to react when they collide, they will simply bounce apart. No reaction will occur. Here's an example of an energy graph. This is for an endothermic reaction. Energy changes in a reaction. I start down here with my reactants. I have about this much energy to start. I only need to get to this much energy at my products, so my products only have a little bit more energy than my reactants do. But I have this giant hill I need to climb to get there. I need to get over the top of this hill like a roller coaster to actually make the reaction begin. That's the activation energy. Even though that energy I don't need at the end, I need it to get started. So this giant hill is the activation energy needed for the reaction, and this change in E is the actual difference in energy between my reactants and products. The angles that molecules collide with each other also matters. It's called a molecular orientation. Collisions must involve enough energy to produce the reaction, must be equal or exceed the activation energy. Relative orientation of the reactants must allow formation of any new bonds necessary to produce products. There's a lot of reactions that would happen, but it's too cold. The temperature needs to be high enough for the average particle to be moving fast enough for the reaction to actually start. Like we said, temperature will increase the rate of reaction by increasing the average kinetic energy of the particles. If the particles have more kinetic energy when they collide, they're more likely to have the minimum energy needed to react. A higher percentage will actually react, increasing the rate of the reaction. Changing temperature will change the rate constant for a particular reaction. The rate constant is going to be much higher at a higher temperature. All of this can be summarized into this weird equation called the Arrhenius equation. It shows the relationship between rate constant and temperature and activation energy. All of this is not something we're ever going to have to solve. This is just kind of a weird equation that helps us understand how activation energy and temperature relate to K. A is called a frequency factor, basically the frequency of collision, kind of a constant you have to determine by doing an experiment. EA is my activation energy, R is my gas constant, T is my temperature. Okay. The main thing I'm looking at here with the Arrhenius equation, K equals, I'm not even going to write the A because that doesn't matter. It has E to the negative EA divided by RT. I ignored the A because it's just a constant. What I want to know is how is K affected when activation energy increases or decreases or temperature increases or decreases. It's not super easy to tell when you have E here. So let's say I'm going to do this twice. K equals E to the negative 1 over, just say this is 10. Doesn't matter. I'm going to increase the second time my activation energy. I'm going to double it and see how that affects my rate. K equals, oh my goodness, E over negative 2/10. What I just did, I doubled my activation energy, leaving everything else constant. I'm going to plug both of these in to my calculator and see what I get. I'm going to do negative 0.1. And I get 0.905. I'm going to do E to the negative 0.2. And I get 0.819. It's higher. Low activation energy, higher rate constant. Okay, this has a lower number up here for EA. Lower activation energy makes a higher rate constant, which makes sense. More of my particles are able to collide with enough energy to overcome and start the reaction, but only if my activation energy is high enough. Now we're going to do the same thing for temperature, right? So I'm going to do over here, K equals E to the negative 1 over, we're going to start with 100 Kelvin. And then we're going to do at, let's see, 1000 Kelvin. We're going to see how it affects it. So the top one, this is at the cooler temperature. It's negative 0.01. My K is equal to 0.9900. The bottom one, and okay, I picked really bad numbers for this, but it's going to come out to 0.9990. Basically, my temperature goes up by 10, my rate constant goes up as well. So when your temperature increases, so high temp, higher rate constant. If I picked better numbers, the effect would be more dramatic, but it is higher. That's what the Arrhenius equation is for. It's just to compare activation energy and temperature to get these two conclusions. Lower activation energy, higher rate constant. Higher temperature, higher rate constant. The inverses would be opposite. High activation energy, lower rate constant. Less of them are able to react. Low temperature, lower rate constant. Less of them have the energy needed to impact each other, cause a reaction. Very last thing we have here is just catalyst. A catalyst is a substance that speeds up a reaction without being consumed itself. A catalyst, the idea, it just helps lower activation energy by orienting molecules in the correct way. Allows collisions to be more effective. How you can think about it is a catalyst just kind of holds one of the molecules in place and allows the other molecule to hit it with maximum energy. Catalysts aren't used up in a chemical reaction at all. You keep them around and they just can kind of keep doing reactions over and over and over. So we're not going to talk a lot about them, but a catalyst in general is just something that speeds up a reaction. It's not consumed itself. All right, that's our last slide for today. Hopefully chemical kinetics wasn't too bad. We kept it under an hour this time, so that's great. Please make sure your Unit 12 notes are complete and turned in to me by the due date. All right, thank you.